Now we will discuss this theorem. Let f be a function from a to b and g is a function from b to c if f and g are 1 to 1, then f composition g is 1 to 1. Second one, if f and g are onto, then f composition g is onto. So to discuss this result, we need the definition of composite function. If f is a function from a to b and g is a function from b to c, then composition is a function from a to c. Here the codomain of f should be same as the domain of g. And how do we find the images of elements of A? It's by using this definition. F composition g of x belongs to A is equal to g of f of x. And one-to-one function says that for all x1, x2 belongs to A, f of x1 equal to f of x2 implies x1 equal to x2. Or we can prove that two different elements from the domain has two different images. And to show the function is onto, we need to show that for every y taken from the codomain, we can find at least one element in my domain such that f of x is equal to y. Or in short, we can say that range of the function is equal to codomain. Okay. Now let me prove this result by using these three prerequisites. Okay, so for the first result, what is given? Given f from a to b and g from b to c are 1 to 1. To prove that f composition g, it's a function from a to c, is 1 to 1. For x1, x2 belongs to A, assume f composition g of x1 equal to f composition g of x2. So this implies from the definition of composition, this is g of f of x1 equal to g of f of x2. Now to proceed further, let me try to understand what we are doing here. So x1 and x2 are present in this set. Okay, and f of x1, f of x2 are present here. G of f of x1, g of f of x2 are present here. So this is our f composition g of x1 and this is our f composition g of x2. So with this is f, it's a function from a to b, and this g is a function from b to c. Okay, and f composition g, we know it's a function from set a to c. Now have a look at this one. These two are equal. Okay, these two are equal. Then obviously we are expecting their pre-images are same. Okay, this implies f of x1 is equal to f of x2. What is the reason? Because g is 1 to 1 function. Since g is 1 to 1, if the images of f of x1 and x2 are same, then their pre-images f of x1 and f of x2 should be same. Okay, now further, f of x1 is equal to f of x2 and f is 1 to 1 function from a to b. So if these two are same, their pre-images must be same under the function f, that means x1 should be equal to x2 because f is 1 to 1. We started with what? We started with the assumption that the x1, so image of x1 and x2 are same, and we proved their pre-images are same under the function f composition g. So that proves f composition g is 1 to 1 function. Second result, given f and g are onto, f is a function from a to b and g is a function from b to c are onto. To prove that f composition g, it's a function from e to c, is onto. Okay, how do we define onto function? So onto function says that consider an element from the codomain, show its pre-image x is present in the domain. So now C is the codomain. Okay, C is the codomain of f composition G. So this is what I'm supposed to do. So now f is a function from A to B. G is a function from set B to set C. Here I'm supposed to consider an element from where? From C. So because C is the codomain of f composition G, let me assume that Z is one element taken from C. Let Z belongs to C. And what we know in this case, G is a function defined from B to C, E is onto function. Since G is onto function defined from B to C, we are expecting its pre-image Z is present in B. So let me assume that its pre-image B, Y. Okay, so this implies there exists an element Y belongs to B such that G of Y is equal to Z. This is equal to G of Y. Okay, let me call this as just result number 1. But what can be noted here? We found Y is one element present in B, but Y is an element present in B. And B is what? B is the codomain of the function f, and f is also onto function from A to B. And f is a function from A to B is onto, which means we are expecting its pre-image x is present in set A. So this says that there exists an element x belongs to A such that f of x is equal to y. Okay, so this is f of x. So y is f of x, so this becomes g of f of x. Okay, so f of x equal to y. Let me call this as result number 2. But the value of y is what? Value of y we found as f of x. So by using result 2 in 1, so we have g of f of x is equal to z. What the definition of composition says? It says that f composition g of x is equal to z. Yes, what we have proved that for every z belongs to C, there exists its pre-image x present in set A such that image of x is equal to z under f composition G. That is, we just proved that for every z belongs to C, there exists x belongs to A such that f composition G of x is equal to z. Therefore, f composition G is onto function. See, so simple. And this just proved that, so whenever the two functions f and g are 1 to 1, their composition is also 1 to 1. If the two functions are onto, their composition is also onto. In general, or in short, we can also put it like this: if f and g are bijective, then f composition G is also bijective. Okay, that's fine. So this is what the theorem number 1 is. So note here, converse of the above theorem is not true. But you can show part of it as a true statement. So that's what this theorem speaks about. The theorem says that let f be a function from A to B and g is a function from set B to set C. Result number 1 is, if F composition G is a function from A to C is onto, then G is onto. Okay, if the composition is onto, definitely we can claim G is onto, but we don't know about the function F. We can't predict about F. If composition is 1 to 1, then we can say F is 1 to 1, but we can't speak about the function G. That is what this theorem says. Okay, let me prove these two results. So once again, very simple results. For the first result, given F composition G is a function from A to C is onto. To prove that the function G defined from set B to C is onto function. Okay, now what I'm supposed to do to prove this is onto function, I need to consider one element from the codomain. So now consider Z belongs to C, which is the codomain of what? The set B. Consider Z belongs to C. We know F composition G is a function from A to C is onto. So this proves X belongs to A such that F composition G of X is equal to Z. So from the definition I can rewrite this one as G of F of X equal to Z. So that is range is equal to G of B is equal to C, because we have clearly said that because this is equal to codomain. So that proves therefore G is onto. Next result. Result number 2. So it's very simple. Given F composition G, it's a function from A to C is 1 to 1. To prove that F, a function defined from A to B, is 1 to 1. Okay, so to prove this result, let me consider. So for x1, x2 belongs to A, assume x1 is not equal to x2. Okay, if x1 not equal to x2, what we know is F composition G is a 1 to 1 function. Okay, please look at this one. Okay, x1 and x2 are the elements from set A, and F composition G, it's a function from set A to C with, so since F composition G is 1 to 1 function, if x1 is not equal to x2, we are expecting F composition G of x1 is not equal to F composition G of x2, because F composition G is 1 to 1 function here. As F is a function from A to B, G is a function from B to C, and since x1 is not equal to x2, their images are different under the function F composition G. That is, F composition G of x1 is not equal to F composition G of x2. So this proves G of F of x1 is not equal to G of F of x2. Okay, this implies, see, so this is equal to G of F of x1 not equal to G of F of x2. Now have a look at this one. If this is the case, can we claim F of x1 is not equal to F of x2? This is what the requirement for me. So for x1 not equal to x2, if it implies F of x1 not equal to F of x2, that proves F is 1 to 1 function, because if the two elements of set A are not equal, then their images should not be equal, so that F becomes 1 to 1 function for us. So can we write this expression from here? That is what the next question is. So we wrote this because F composition G is 1 to 1. Now we can write this one because of one reason. This comes from the definition of composition, and this step comes from the reason. Now have a look at this one. F of x1 not equal to f of x2. Suppose if these two are equal, what happens? If these two are equal, G is a function defined from B to C, and we have already written these two are different. Now if these two are same, a single element P will be having two images. It is not true for the definition of a function. So because G is a function defined from B to C, okay, G is a function defined from B to C. Because of this reason, so these two cannot be same. When these two are different elements, these two should be different. So initially we started with what? We assumed that x1 is not equal to x2. Since F composition G is 1 to 1, we are expecting their images are different under this function. We rewrote this in this form by using the definition of composite functions. And next we wrote this one as f of x1 not equal to f of x2, because if these two are different, we are expecting these two has to be different. Otherwise a single element will be having two images. That is not true for a function. Therefore f is 1 to 1 function. Next theorem is a function f from a to b is invertible if and only if f is bijective. Okay, let me prove this result. It's a very important result from the point of your examination. That's very simple one. Okay, first part is given f from a to b is invertible, which implies there exists a G from B to A such that F composition G is equal to IA and G composition F is equal to IB. So this comes from the definition of invertible function. Here I need to prove that F is bijective. For this, first we need to show the function is 1 to 1. F is 1 to 1. Okay, to show the function is 1 to 1, so what I am supposed to do? For x1, x2 belongs to A, consider f of x1 equal to f of x2. Okay, now let me just consider the sets A, B and the set A. Okay, f is a function defined from set A to B, and I'm just considering one more function G, and G is a function defined from B to A. Now x1 and x2 are taken from the set A. I am assuming f of x1 equal to f of x2. Okay, so what I'm doing here, for x1, x2 belongs to set A, I have assumed that f of x1 is equal to f of x2. Here I need to show that x1 is equal to x2. So to prove that, so since G is a function from B to A, so we are expecting that image of f of x1 and image of f of x2 must be same. Okay, that is G of f of x1 must be same as G of f of x2, because if these two are different with these two are same, a single element will be having two images. That is not true for a function G. Because G is a function, I can rewrite this one as g of f of x1 is equal to g of f of x2, because g is function. So look at the reason, because g is function. So this implies, this comes from the definition now. Definition of composition says f composition g of x1 is equal to f composition g of x2. But what we know is f composition g is nothing but what? Ia. This is given. This implies Ia of x1 is equal to Ia of x2. This comes from the definition and this comes from the given. That is, the function is invertible, that says f composition g is equal to Ia. So Ia of x1 is x1, Ia of x2 is x2. We started with an assumption that f of x1 and f of x2 are same. Finally, we proved that this x1 and x2 are not two different elements, they are the same. Okay, so hence the function f is 1 to 1. Now let me talk about onto function. F is onto. So to prove this, so I need to consider an element from where? From the codomain. So let B be an element taken from the set B. Okay, so let B be an element taken from set B. So this says that G of B belongs to set A. Okay, let me put it like this. So I'm just writing the function G first. Let me assume G is a function from set B to set A. So now since I've taken B is an element from set B, so image of B, G of B is present in set A. Okay, now, and we can note that, so B can be written as IB of B. So because IB is an identity function defined on B, so image of B is itself. So IB, I will just replace this IB by, IB is nothing but what? G composition F. So G composition F of B. So this is equal to F of G of B. So what we have proved here, and you can note here, so F is a function from G of B, function from set A to B. Its image is F of G of B. So that is present in set B again. So we can note that, that is, for every B belongs to set B, there exists G of B belongs to set A. Okay, for every B, this is equal to B. Okay, for every B belongs to set B, we can find G of B which is present in set A, such that F of G of B is equal to B. So therefore F is onto. It's so simple. Let me just repeat it. I have taken an element B from set B. So obviously its image will present in what? Set A, because G is a function from B to A. And I'm interested in the function F, not in the function G. Now I need to bring the connection between F and G. For that, what I have done here, I'm just considering the function F, which is defined from A to B. Since G of B is present in set A, its image has to present in set B, that is F of G of B, which should be equal to, which is equal to B. That is what we got here. F of G of B is equal to B. So what we can note then, so for every B belongs to set B, we can find its pre-image G of B is present in set A, such that F of this element is equal to B. So that is what the definition of onto function, that proves the function F is onto. So therefore F is bijective. Now converse of the result. Conversely, given F from A to B is bijective, to be is bijective, we need to prove that F is invertible. We need to prove that F from A to B is invertible. So what I need to do here, so I need to identify one function g from B to A such that F composition G becomes IA and G composition F becomes IB. Since F from A to B is onto for every B belongs to set B, there exists A belongs to set A such that F of A is equal to B. Let G be the converse, let G be the converse of the function F from A to B. Now, since F from A to B is bijective, F from A to B is bijective, so we have cardinality of A is equal to cardinality of B, and every element of B has unique preimage in A under F. So this implies G is a function from B to A. Okay, so what does it says? This says that if F is a function from A to B and you write the converse of this G, since the number of elements in A and number of elements in B are same, every element of B has unique preimage in A under the function F, means we can note that it is saying something like this. So A is the element here, B is the element which is present here. So F is a function defined from A to B and G is the function defined from set B to set A. Now if image of A is B under the function F, then image of B is A under the function G. So this is what happens, that's what we are saying here. So this implies G is a function from B to A such that G of B is equal to A if F of A is equal to B. Now we have found a function from set B to A. Now I need to show that further need to show F composition G is equal to IA and G composition F is equal to IB. So that proves the function. So that proves the function G is inverse of the function F. Okay, is it possible to show this? Let me check. If I consider F composition G, so definitely F denotes its domain, G denotes its codomain. So A and A, it's a function from A to A. So domains and codomain are matching with the identity function on A. And if I consider G composition F, so G has to denote domain and F denotes its codomain, it's once again B. So the domains and codomains are matching with the identity function on B. Now let me consider F composition G of an element A belongs to set A. So this says that G of F of A. So this is G of F of A is given by what? B. So G of B is given by what? A. And A is an element taken from where? From set A. Okay, for A belongs to set A, this happened. So if this is the case, I can rewrite this one as IA of A. Because since A is an element of the set A, image of A is A under IA. So we proved that for these two functions, domains are same, codomains are same, and they are acting same on every element of the domain. Now for B belongs to set P, consider G composition F of B. This is F of G of B. This is F of G of B is equal to A, F of A is equal to B. So B can be written as what? IB of B, because IB is an identity function defined on B, and B is one element present in set P. So IB of B becomes P. So we proved for these two functions domains are same, codomains are same, and they are acting same on every element taken from the domain B. So that proves, so therefore G is inverse of F, hence F is invertible. Now let me see a second theorem on invertible functions. So this is what it says. If F from A to B and G defined from B to C are invertible functions, then F composition G defined from A to C is invertible. And F composition G whole inverse is equal to G inverse composition F inverse. It's a very simple result again. Given F from A to B and G from B to C are invertible functions. Okay, so this proves F and G are bijective functions, because we know that invertible functions are bijective functions. F and G are bijective. This implies F composition G, it's a function from A to C, is bijective. So one more theorem which we have proved. If F and G are bijective functions, their composition is bijective. So this is a new function H for us. So if the function H from A to C is bijective, so then that function becomes invertible. So this implies F composition G is invertible, because every bijective function becomes invertible function. This proves the first part. To prove the second part, let me consider this. Let F power minus 1 and G power minus 1 be inverses of F and G respectively. So what is F power minus 1? It's a function defined from B to A. F is a function from A to B. So F power minus 1 is a function defined from B to A, such that F inverse F composition F inverse is equal to IA, and F inverse composition F is equal to IB. And G is a function from B to C, so G inverse is a function from C to B, such that G composition G inverse is equal to, for G domain is B, so it's an identity function on B, and G inverse composition G is equal to, for G inverse C is the domain, it's an identity function on set C. Okay, we have this. Now we need to prove that. So to prove that, so F composition G inverse is equal to G inverse composition F inverse. Okay, so first, is it possible to do this? Let me just check that first. So inverse of F composition G. It is basically what? It is basically a function from set A to set C. Okay, let me call this one as H. It's a function defined from A to C. And let me call this one as K is what? G inverse composition F inverse. So we just check out its domain and codomain. Is it possible to find this? Let me just see. G inverse is a function from C to B. F inverse is a function from B to A. So it is possible to find G inverse composition F inverse, where G inverse donates its domain, that is C, and F inverse donates its codomain, that is A. Here we need to show, H composition K. So for H the domain is A, it's an identity function on A, and K composition H is equal to identity function on C. This is what needs to be proved. Let me consider the first one. So consider H composition K. This is equal to, so what is H composition K? Let me substitute H and K values here. So K is given by, so G inverse composition F inverse. So we are taking the composition with what? H. So H is given by F composition G. Okay, we need to show this is equal to IA. Let me try to prove this one. This is equal to, so we know that we can just place the brackets wherever that we want. So I will rewrite this one as F composition G composition G inverse, its composition with F inverse. So I will just group these two together. So G composition G inverse, it is given by what? It is equal to IB. So it is F composition IB composition F bar minus 1. Now it is left to me. I can combine this IB with F or IB with F bar minus 1. Okay, let me combine it with F itself. F composition IB, its composition with F bar minus 1. Okay, this came from the associative property. Okay, this came from the definition of inverse. This came from the definition of inverse. So this is the rule I have used here. G inverse composition, G composition G inverse is equal to IB. And this is once again from the associative property. And for a function F defined from set A to B, we know that F is equal to IA composition F and is equal to F composition IB. So F composition IB is nothing but what? F. So it is F composition F inverse. F composition F inverse is equal to what? IA. So this is what I wanted to prove. So that's done now. It's an identity function on A. First part is done. So consider next one, that's K composition H. K composition H, it is equal to, H is given by F composition G and K is given by G inverse composition F inverse. So just like the previous result, by using associative property, I will combine F and F inverse by using associative property. So G inverse composition F inverse composition F is nothing but what? IB. It is IB composition G. Now I can group once again by using, this is from the definition. So now by combining these two or by combining these two, let me combine this with G itself. Okay, this came from associative property again. And since G is a function defined from set B to C, okay, G is a function defined from B to C. Yes, it's a function defined from B to C. So G is equal to IB composition G, and it is also equal to G composition IC. But we have IB composition G here, that becomes G So G inverse composition is once again comes from this property. Okay, so G inverse composition, G is given by what? IC equal to IC. So this is what we had to prove in this case. Okay, we had to prove K composition H is equal to IC. We proved. So therefore inverse of H is K, that is inverse of F composition G is equal to G inverse composition F inverse. Therefore that is nothing but F composition G whole inverse is equal to what? G inverse composition F inverse. So this is what we had to prove in this case. Now just have a look at this result again. Let me see what we did here. The first part is, so F and G are invertible, that says F and G are bijective. So composition is definitely bijective, we know this result. If the function is bijective, obviously it becomes invertible function. So here proving this part is the major part. Here F inverse and G inverse are inverses of F and G means, so F and G satisfies these two conditions with F inverse and G inverse. Now I just need to show that inverse of F composition G is equal to G inverse composition F inverse. For that I need to show this H composition K is equal to IA and K composition H is equal to IC. Because here I need to show that K is a function defined from C to A such that K and H together satisfies these two conditions. So I consider H composition K. So with the help of associative property and the definitions of invertible functions and this property of the function F with the identity functions on domain and codomain, so we have proved these two results, and with these two results we can claim that so H is inverse of H is K, that proves F inverse of F composition G is equal to G inverse composition F inverse. Okay, that's all. Thank you all. If you have any doubts, so call me.